Thank you all for coming. I know today is a very difficult day with all kinds of things going on. So some of you had to make special arrangements. So it's a pleasure to welcome Dr. Stefan Danilishin today. He had a tough time getting here. His flight connection was missed. He had to spend time in Detroit last night. So Dr. Danilishin is one of the leading specialists in the area of quantum noise and quantum measurement in precision interferometry, in particular in gravitational wave detection. He got his PhD from the Lomonosov Moscow State University in 2005, and this is a famous group led by late Professor Vladimir Braginsky, some of you probably know, under the supervision of Professor Farid Khalidi, who is currently very active. And we are also the co-author of this very famous textbook called Quantum Measurement. Currently, Stefan is the leader of the junior research group called Quantum Optomechanics at the Albert Einstein Institute for Gravitational Physics, Hanover, and the chair of the LIGO Scientific Collaboration Quantum Noise Workgroup. That's how I know him very well, because I attended a teleconference with him in 2 months. So, before moving to Germany, there was a series of postdoctoral and faculty positions at the Moscow State University, University of Western Australia, and the University of Glasgow. He's published a lot of papers, more than 100 scientific publications. Also, several new techniques for non-demolition schemes for gravitational detection. He's also known for 2 very famous papers. These are review articles in the living relativity, and one of them is called Quantum Measurement Theory in Gravitational Detectors. This was published in 2012, and my student, I have often consulted that paper, so I know how important that is. There also a very recent one called Advanced Quantum Technologies in Gravitational Detectors. And both of these are like seminal papers that people have to consult to prepare. So let's welcome, and he's going to talk about new technique for detecting gravitational waves in the 3rd generation light.
Thank you so much. Thank you, Celine, for this nice introduction, and thank you all of you having me here. It's a great honor to be in the Northwestern University and in CIERA. So yes, today I will be talking about the future of the gravitational wave interferometry. So, as far as I understand, many people here, the majority are working on the data analysis of the data from the existing interferometers. And I will be talking about the plans for the 3rd generation detectors, and in particular one variant, the speed meters, that I personally, doing research on it, think is the most suitable scheme to be implemented in the next generation detectors to improve their sensitivity, particularly at low frequencies where most of the interesting astrophysics going on. Okay. So this is the outline of my talk. So if I go astray a little bit, so don't blame me too much. I was preparing this talk in the aircraft, at the same time thinking hardly whether I will make my connection from Detroit to Chicago or not. It turns out that I didn't. So anyway, so I will start with the motivation for this research. Then I will talk about why actually quantum noise and quantum limit on sensitivity is important for gravitational wave detectors, how it is related to gravitational wave Hall. And then I will jump to the speed meters and tell what it is, how it works, and all the interesting research which has been done since the inception of this idea. And with the help of the Holy Spirit, I will probably come to the conclusion in time. Okay. So, everyone here, I think, is familiar with this picture from the discovery paper. But what I wanted to tell with it is that actually we will know much more information from the gravitational wave signal, in particular of the binary black hole or the binary neutron star, if we can see further in the past of the process of collision. So the earlier we detect the start of the spiraling towards the merger, the more information we get, the higher will be the signal-to-noise ratio of our detection, and the higher will be the precision of the parameter estimation. So, and that, actually looking at the shape of the waveform, which you are much more familiar with than I am, you can see that the frequency is actually getting lower and lower if we go further into the past of this process, and therefore it means that we need to improve the sensitivity of gravitational wave detectors, in particular in the low frequency region. So, and you know that currently the sensitivity of gravitational wave detectors, of LIGO detectors and Virgo detectors, is limited at low frequency at approximately 50 hertz by different noise sources, in particular seismic noise and suspension thermal noise. But it is closer and closer as LIGO is going to its design sensitivity, to the point when the dominating noise will be the noise generated by the quantum nature of laser light being used in LIGO as a main measurement medium. Okay, so I don't know how many times you have seen this like that, but probably numerous. So what I wanted to say here is that, yes, so the gravitational wave, if considered in the local Lorentz frame of the beam splitter, can be considered as the kind of force, tidal force, which changes differentially the length of the arms of the interferometer. But from the point of view of the measurement theory, what this device is doing, it is trying to evaluate the phase shift, or basically to measure the phase which is induced by the motion of the mirrors, presumably created by the gravitational wave. So this is an ultra-precise phase meter from the point of view of the measurement theory or interferometry. So, and the question is there any fundamental limitation to the precision with which we can measure phase? And it turns out that actually, yes, if we look into the nature of light, or the laser light that we use in the interferometers, and as quantum mechanics, so this is where quantum mechanics meets general relativity and gravitational wave detectors. So the quantum mechanics tells us that light is a quantum entity, and it's at the same time a flux of particles and a wave, but the main collateral of that is that we cannot know the fundamental, the canonical observables of the light with the ultimate precision simultaneously. And the canonical observables in the case of the wave processes, or electromagnetic wave, is the phase and the amplitude of the light. So there is an uncertainty relation which connects the uncertainty of the phase you can have and the uncertainty of the amplitude or power of the laser light used. And as such, it means that if only you don't have an infinitely uncertain in energy source of light, you cannot have sensitivity to the phase as small as 0. That's that way. So, and basically what you will see at the output of the gravitational wave detector is the spectrum like this, where the central peak is basically the carrier of the laser. So this is the frequency of the outgoing light. And these are modulation sidebands, which actually contain the signal, because these modulation sidebands are created by the mirrors modulating the phase of the outgoing light. And the shape of this sideband is actually the signal we want to measure. And this hairy stuff on top of it is the fluctuations of the fundamental fluctuations of the laser phase and amplitude that covers our signal. So radiation depicted here is, of course, very idealistic, so it's very high signal-to-noise ratio. In reality, it's mostly noise, and it takes quite substantial skill that you guys have to dig out the signal, gravitational wave signal, out of this house. Okay, so this is also the plot which many people here have seen innumerable times, and this is the design sensitivity of gravitational of LIGO detectors. So the black curve is the total sum of all the noise sources that beset gravitational wave interferometer, and you see that when it reaches the design sensitivity and the input power of the laser finally reaches the 125 watts, what you will have is that in almost all frequencies, the sensitivity will be limited by this magenta curve, which is the quantum noise. And this quantum noise consists of two parts. So the first one, which pertains to the fluctuations of the phase of the laser I was talking about before, is the shot noise, and this is dominating at the frequencies, high frequencies above, let's say, 60 hertz. And the lower part, you see this kind of raising wall, magenta wall here, it is known as quantum radiation pressure noise. And this is a direct consequence of effect which is known in measurement theory as quantum back action. When the system you're using to measure some parameter, in this case the displacement of the mirrors caused by the gravitational wave, is also disturbing the measured quantity. I will talk about it later in more detail, but basically what this plot should tell us is that it is already now, we are close to the situation when the gravitational wave detection precision and the signal-to-noise ratio will be limited, or is limited, by quantum noise at almost all frequencies. And if we want to reach the goal or reach the design sensitivity of the advanced detectors, which has to be at least order of magnitude better, we need to use some witty tricks to actually go below this magenta curve, to do something to modify this curve in such a way that it goes down. So, and this calls for the what is called quantum non-demolition techniques, QND techniques, a very fancy word which resonates very well with the aspirations of the fun dimension. Okay, so once again to the quantum noise. So if you look at the laser line, then the coherent sinusoidal wave at the oscilloscope will have such an oscilloscope at the optical frequency will look like that. So the classical electrodynamics predicts what is depicted by this dashed red line, and quantum mechanics says that fluctuations of amplitude and phase should be creating these pairs around. And if you plot it on the phase plane, where here is the amplitude and phase quadrature of the light, then what you will get is the phase picture, which is for the red line, will be just this arrow, which rotates counterclockwise. And the quantum uncertainty around this will be depicted by this fuzzy blob, this cloud of possible outcomes of the measurement if you try to measure the phase and amplitude of the laser light many, many times. That is what you will get as a result of quantum mechanics. So, and yes, so this is the uncertainty relation I was talking about between the phase and amplitude. And then, how precisely we can measure the motion of the mirror, which is the element, the simplest element of the gravitational wave detector. The real gravitational wave detector is, of course, way more complicated than a single mirror, but that is sufficient to understand. So to monitor the motion of this mirror, we need to measure phase very precisely. I said this already. So, and how do you know whether the mirror has moved or not? So if the mirror moves, it modulates the phase, so it adds the phase to the outgoing light, to the reflected light, which is proportional to the displacement of the mirror. The displacement of the mirror is caused by gravitational waves is much smaller than the wavelength, of course, of light, and we need to detect this small phase shift. So how does it behave on the phase plane? So actually this fuzzy blob, which is rotating with the optical frequency phase and amplitude phase space. So if you have additional phase shift caused by gravitational wave, it will make the this fuzzy blob to advance or to lag compared to the unperturbed, non-moving kind of signal, the reflected light. So, and the task to measure this motion will go down to distinguishing whether this fuzzy blob has moved or not. And this is apparently only possible if the distance between the centers of the non-perturbed and perturbed, the signal, the motion with the signal, the centers of these fuzzy blobs are located at the distance equal to the size of the blob. So if it is less than the radius of this blob, then apparently you cannot distinguish. So, and this is basically the picture of how quantum short noise is working. So basically the limit is the angle that corresponds to the distance between the ends of these arrows equal to the diameter of the fuzzy blob, which is defined by the fundamental uncertainty phase of the laser light, of the coherent state. So this is it, but is this the only thing? Well, were it only this, then the sensitivity of quantum noise limited sensitivity gravitational wave detector will look like that. It will be flat at the frequencies below the bandwidth of the detector and will go up because of the finite bandwidth of the detector at higher frequency. So, unfortunately, this is not the full story. So here, we have to actually go a little bit deeper into the analysis of the motion of the mirror and interaction of it with the light. And we should recollect that light is at the same time as a flux of photons, which can be represented by these nice balls kicking the mirror as they reflect off. And while kicking the mirror, so they transfer the momentum to it in a random way. And this transfer of momentum makes the mirror shake. And the shaking of the mirror is actually can be taken for the signal, for the gravitational wave. This is what is called the back action or radiation pressure noise. And you can see that unlike the short noise, where it can be made smaller if you increase the power of or basically the amount of photons which is sent to the mirror, because the length of this stick becomes longer as you increase the number of photons, and then you can discern the smaller angle. So that's why the sensitivity, the short noise limited sensitivity is inversely proportional to the power of the used light, or to the number of photons which you send to measure this. But the radiation pressure noise, or basically how much the mirror moves as it is hit by the photons, it's directly proportional to the number of these photons. So we have a kind of trade-off situation when one source of noise is inversely proportional to the power and another contribution is directly proportional to the power. But they also have a different frequency dependence. You remember that the shot noise doesn't depend on the frequency below the bandwidth of the cavity if there is a cavity. No cavity, so we have to consider here. But the radiation pressure noise actually does depend, because the force which photons, random force, impose on the mirror, its spectrum is flat. But the response of the mirror is different at different time scales. So the massive object has inertia, and the faster is the applied force, basically the higher is the frequency, the more difficult it is to move it. But if the force is applied slowly, then you can move the mirror to much larger amplitude. And that's why at lower frequencies, the radiation pressure noise becomes larger, and it actually depends on frequency as 1 over omega squared. And this is exactly the susceptibility of the inertial mass in the frequency domain. So it is bonding to the force as 1 over frequency squared. Okay, so if we put these two things together, what we get this kind of trade-off situation. The shot noise and radiation pressure noise produce this kind of curve. If you want to increase the power, the shot noise will go down, but at the same time, radiation pressure noise will go up, and the whole curve will just slide along this locus of points, which is identified as SQL, and these 3 letters stand for the standard quantum limit, which was first predicted by Braginski, that says that if you don't do any tricks, then just increasing power or decreasing power, or even using squeezing, as it turns out, frequency-independent squeezing, you cannot go below this black line. And the whole point of the research being done in the Moscow State University and in many other places in the world now is to contrive a scheme that will allow to go below this black line and thereby increase the sensitivity of the gravitational wave. Okay, so what is the problem with the current detectors? So they are Michelson interferometers, and as Michelson interferometers, they measure the displacement of the mirrors. And this leads to the SQL. So from the point of view of quantum measurement theory, that is because displacement of the mirrors does not commute with itself at different points at different times. And that says that you cannot measure it precisely, and leads to the SQL. So, but already in the 30s, John von Neumann introduced the concept of the quantum non-demolition measurement. Says that there are observables which are not disturbed by the measurement, and they call quantum non-demolition ones. And one of them, for the free mass, for instance, consider the freely suspended mirror, is the momentum. So momentum is a conserved quantity of the free mass, and it can be shown that thereby it is commuting at different times, and therefore there is no back action. So this was the basic idea behind the speed, because momentum is proportional to velocity. So this idea was taken forward by these two gentlemen, Professor Vladimir Braginski and Galili, in the 90s, where they proposed the first speed meter, which they thought will help to fight the back action loss. So the history goes like that. So this is the initial, so you see the quality of the scientific illustrations at that time. Actually, it's very stylish. And they were proposing this scheme for the bar detector at that time. So therefore, what you see here, these two squares, is maybe surprising, but this is the two microwave cavities. So, and this M here is actually the bar detector, or the vibrational mode of this huge metal bar. And what they propose is that if you create two coupled cavities, and one of them is coupled to the motion of the bar detector, so the size of this cavity and wavelength, resonance wavelength of this cavity can change. So what will happen if you have the pump to another cavity, because of the coupling, the energy, the microwave energy, will slosh between the two cavities. And if you tune your coupling in the right way, so at each sloshing period, the phase of the microwave going into the second cavity will flip side. And they said that that actually realizes the concept of measuring the displacement of this mass M at a sequence. So you basically measure the differences of the displacements at the time interval given by the sloshing frequency. And since the phase flips sine, so you take basically the difference of the displacements. And the difference of the displacements at two different times is proportional to the mean velocity. So it will become more clear, because this is actually a horribly complicated scheme, this one, and the optical realization of it to understand the speed meter. So therefore, in 2002, Perdue and Chen proposed, okay, so this was the sloshing one, no, in 2003, Chen actually showed that, Yang Chen showed that Sagnac interferometer is also a speed meter, and its action and why it is a speed meter is much easier to understand. So, and then in 2004, I proposed, so the original proposal of Yan Bei involved some ring cavities, which all the experiments hate. For good reasons. But, well, for all practical purposes, for you, I'm also an experimental person. Yes. So, I actually, as a main part of my PhD thesis, was working on the scheme of the Sagnac speed meter, which doesn't use the ring cavities, but rather use the linear cavities. But instead, you have to deal with the polarizations. So, okay. So, this is my interpretation of how the sloshing speed meter, these two squares, microwave squares in the optics work, and how the Sagnac speed meter. So this is a zero-area Sagnac interferometer. You know the Sagnac interferometer is being used in gyroscope to measure the rotation. So if you think about this mirror being flipped back here, so it will be a Sagnac, basically a ring. And light from the laser goes in two directions, clockwise and counterclockwise. So the red one is the clockwise, so it basically reflects here and goes like that and comes back. So, and the blue one goes in the opposite direction. So now, if you think about the displacement caused by the gravitational wave, for instance, so this is x and xn. So the phase of the light traveling in the clockwise direction will depend on the motion of the mirror at the point of time t, and then after the time which takes the light to travel between the mirrors, it will be the contribution from the motion of the east mirror. So the signal which goes only from the clockwise beam to the photodetector will be this sum. But for the counterclockwise one, it will be the opposite order. And at the beam splitter, at the readout port, where you measure your gravitational wave signal, the photocurrent will be proportional to the difference of these two phases. Just because yes, so the clockwise one being reflected off the mirror acquires the phi phase shift. That's why this was minus. So if you look at the difference of these two signals, you will see that you have a difference of xn at time t at xn at time t plus tau. And with the inverse sign, the same difference of the east mirror one. And this difference, if you make a Taylor expansion in tau, because it's quite short, will be the mean velocity of the mirrors. And the outgoing photocurrent will be proportional to the differential velocity of the two arms. So that is how this thing is the speed meter. So the output of this device is proportional to the difference of the differential velocity of the mirrors. So why is it good? So in principle, you can't say that it's obvious that this is good, because velocity at low frequencies produces much smaller response. Oh, because velocity in the frequency domain is the multiplication by the frequency. Yes, and if frequency is small, that means that the response to the motion of the mirrors will be actually waning as frequency. While for displacement, the response function is flat to the DC, which is supposedly good. So you want to have higher response.
What do you mean by response?
So basically the response is how the motion of the mirror at different frequencies is transformed into the phase of the outgoing light. Transfer function. From the motion to the phase. Sorry?
Why is it dimensional? Shouldn't that be a 1 over?
Well, this is the yeah, sorry. So this is actually plots for already recalculated to the straight. Yes. So yes, if I were talking about see, so basically all of these curves are for the already recalculated into the straight. So it's delta L over L. So if we look at the even simpler scheme of measuring the velocity of the mirror, when you send light to the mirror, it reflects once, and then after the delay, it reflects for the second time from the rear surface of the mirror. Apparently, the phase of the outgoing light will be proportional to velocity. Then you will notice that back action, the kicks of the photons, which are transferred to the mirror, are partially compensated because they are kicking in the same photons are kicking in the opposite direction. And as such, the radiation pressure force in this kind of setup will have this multiplier, which is the frequency of the applied back action force, and tau is the time delay. So it will also be reduced at low frequencies. And that is illustrated on this plot. So basically, if we look at the fluctuations of the outgoing phase from the point of view of quantum noise, the Michelson interferometer, as I told you, so because of the inertia of the mirror, it just goes as 1 over frequency squared at low frequencies. But because of this term, I omega, for speed meter, it remains flat. So you see, here is 1 over f squared, and here is the frequency to the first power and frequency to the 0 power. So the strain sensitivity is obtained by dividing the fluctuations of laser light by the response of the mirror. Yes.
That's the frequency at which.
This frequency. So this is actually calculated. Yeah. So it's not clear from here. So this is frequency or the bandwidth of the interferometer. You can say that this is the inverse frequency, inverse arm cavity finesse. It's ring down time. So it's not important here. Yes. So, and if you divide this blue curve of the noise by the response, then it turns out that, because here is a f to the first power, and here is f to the 0th power, so you have at low frequencies where back action is dominating, for the speed meter, the curve which is just lying along the SQL, while for the radiation pressure noise of the Michelson interferometer, you have 1 over f squared, and here is 1 over f dt. And this triangle is the region where speed meters help to improve sensitivity of gravitational wave detectors. It has also an additional bonus that in the Taniak interferometer, if you think about this, so in Michelson interferometer, half of the light of the laser goes in each of the arms. In the Taniak interferometer, actually the full power of the laser goes into each of the arms because it is clockwise and counterclockwise. So you have twice the same power for the same input power of the laser. And therefore, you have improvement at high frequency.
Can I think of this as detecting H dot?
Yes, I think. Yes, you can for the free.
So then, from like, I guess like if I just took the voltage of the photodetector and computer, then I would have to.
Well, you anyway have to do it. This is what actually this response functions are sending. So this is how you convert the photocurrent.
Yeah.
Amperes.
As opposed to in the Michelson, you would not have to.
No.
Integrating. Because the Michelson response is flat.
Yes.
So like since you're measuring H dot versus H, like in Michelson, the current I of t is just H of t.
Yes. This is, as I say, what this is shown in frequency. So if you divide by this will be exactly the integration. 1 over f is the integration. Okay, so if we come to the more realistic interferometers and take into account the different loss and noise sources, these are the results that you can get for LIGO parameters, 4 kilometers, and for the Einstein telescope parameters, which is 10 kilometers. The plots obtained in the time when there was no cosmic exploring. And you can see the advantage. So basically, the lower plots show the improvement factor of the red curve with respect to the blue curve. So basically, the ratio of the two at different frequencies. So this is another argument in favor of speed meters. So this is how much you can gain. And this is the astrophysically meaningful quantity. Basically took the function calculating the effective range for the equivalent Michelson and Taniak interferometers, and plotted this dependence on the companion. I start to forget words. Components of the binary black hole and their mass in the solar mass. So you can see from the numbers here that speed meters, first of all, are more sensitive to the higher solar masses components, and also for the same parameters, they produce much better result, which is illustrated by the ratio of the two plots above. So this is the improvement factor, I think, in units. So it's not, it's actually in detection rate. Have to do the average. So, and you can see that you can get up to 300 times, of course it is an extreme, but in here, for example, for the same mass of the components, you will get an improvement of 150 times in terms of the detection event rate. And we have published a paper about how to make this in the high gravitational interferometer recently in the Slide Science and Application, but you never heard about this journal. Very surprisingly, it's one of the Nature journals proliferate. So there are so many of them. And this one, although I also never heard about it, has an input factor of 13. Very surprising. Okay, so what is the problem with the speed meter? What is the problem of speed meters when it comes to the experimental implementation? First of all of the initial proposals, which are shown here, the Chen's Sanyak interferometer with the ring cavities and the sloshing speed meter again, Purdue and Chen. So they have, from the point of view of experimental people, too many additional optical elements, which is very difficult to control, and all of these magic words like mode mismatch, which you probably heard, and which basically for many years has shut me down completely when I was giving a talk to the experimental audience, and they were saying, what about the mode mismatch? So I had absolutely no idea what to answer to that. Now actually I did. So I evolved. So basically these schemes are too difficult to implement. And experimental people don't want to invest into something risky before they get evidence, something incarnate, that shows that it is working better. Therefore, it is important, very important, to do the prototyping of this meter kind of setup to show that these speed meters indeed get better sensitivity and quantum noise limited sensitivity at low frequency than the Michelson interferometers. And for that, there are two prototypes being under construction in Glasgow, in the University of Glasgow. One is the 1.4 meter tabletop Sanyak interferometer, and the second one is the 10 meter polarization Sanyak speed meter, based on my idea of 2004, also in the current 10 meter infrastructure of Glasgow. Okay.
Stefan,
Yes.
So, the Sanyak approach was first proposed by Bob Bayer and group, and then it was not pursued at that point, and not sure why. But as you also pointed out, the Sanyak interferometer has vanishing signal at DC and low frequency.
Yes.
So, in your analysis of how things get better at low frequency, is that taken into account that as you go to very low frequency, the actual signal disappears?
This was actually the problem of the initial Bob Bayer's proposal, because they didn't consider radiation pressure or backaction noise, because at that time it was not a problem. It was not considered a problem.
Right.
The LIGO interferometers, because it was covered completely by seismic noise and thermal noise, and so nobody was thinking about it. And if you don't only consider the short noise, then of course speed meters, and it was not considered as a speed meter, have absolutely no advantage whatsoever, even worse. They have a disadvantage, because at low frequencies, you cannot control them. You don't have an error signal, because there is no signal of the motion of the mirrors at DC. So that's why it was considered as a dead end, only until the quantum nature of light and the radiation pressure and projection was taken into account. And then it turned out that actually, if you are sensitive, if the device is sensitive enough to see that radiation pressure, it will limit your sensitivity, and you have to do something with it if you want to go below this.
But what I was asking is the actual signal itself would go to zero as you go to very low frequency.
But noise goes to zero
as well?
faster.
I see.
That is why you
so
have
signal to noise ratio still improves. Okay.
Yes. Okay, so this is this is actually the scheme of the Glasgow tabletop experiment, and the idea was to show that for the equivalent Michelson, which is the blue curve here, you will have higher quantum noise than the total noise of the speed meter interferometer, which is shown here. It is still on the way, and actually what we learned in these 7 years of building this interferometer, very long, kind of long-term kind of business, building the gravitational wave interferometer, as you know probably, is actually, this is probably the worst of building a speed. So we encountered all possible problems and identified them, but now we understand much better how actually we should build a speed. Okay, so this is just to impress. This is to date the full, or more or less, full tour of the speed meter configurations which have been proposed so far. And the 3 on the top are actually the original one from the year 2000 and 2004. So this is the polarization-based one. And these are the new ones which we developed. And I will be talking about the last 2. Probably already quite exhausted. So yes, so you cannot explain it, the underlying problem, but you know that works, and you don't change the course of action. Okay, so the 2 interferometers I was trying to impress you with are these 2, and what is actually so impressive about them, apart from the very nice colors I use here, is that if you look at them, they are not different from the Michelson interferometer so much. So basically a Michelson interferometer with a 4 kilometer or 10 kilometer or 40 kilometer arms, so the whole infrastructure of the gravitational wave detector remains intact. There is, of course, a catch. For example, in this interferometer, this is the small addition to the output, where you have a quarter wave plate which deals with the 2 polarizations, polarization beam splitter and the mirror. And this thing is making the following basically. So the quantum noise which is coming to the dark part of the interferometer, which is coupled to the signal, to the motion of the mirrors, so it is taken by 2 polarizations. And due to this, as we call polarization circulation unit, you can send the signal coming back of the interferometer, which carries the information about the displacement of the arms. So it goes here, reflects because of the polarization beam splitter to the PCM, to the mirror, totally reflective mirror, and comes back to the interferometer before it goes to the detector. And after it comes back to the interferometer, it actually gathers the displacement at a later time. And tuning the phase of light here, you can also tune the sign with which this signal will come back. And you have, again, the double measurement of the displacement at 2 different times, which is velocity. So and this is how you get, again, the speed meter sensitivity. So because of the lack of time, I will not explain the EPR. By the way, how many people know what is EPR standing? Oh, okay. Yeah, so I always thought that this is, everyone knows that it is Einstein-Podolsky-Rosen. But currently this knowledge is confined to the quantum optics community, where this is a big thing. So this is the underlying fundamental experiment proposed by Einstein to show the quantum correlations and the gist. What is the quantum correlation versus the classical correlation? So, so this one uses these three letters, mainly because it is fast. But there is quantum correlations invoked in here as well. But as I said, there is no time for that. So this is the explanation which I have already given, but in a larger scale. So you can see this polarization circulation speed meter in more detail. You can see how the polarization, p-polarization turns to the clockwise polarization, then circulates in here, then comes back, and the photovoltaic plate turned it into S polarization. S polarization is reflected from the PS, and therefore it goes back. And when it goes through the photovoltaic plate once again, it is transformed into the magenta counterclockwise. This one travels to the interferometer once again, gathers the information about the displacement second time, and when it comes back, it is transformed to the red one, yes, to the red one, which is the p-polarization, and goes out and being measured.
So you did not show the second one, but so this is compatible with the signal recycling meter as well?
Sorry?
When you have the signal recycling meter in the dark code,
Yes.
so it works even in that situation?
Yes.
Okay.
Okay, and this is to show that we're serious people and not only tell that, oh, this is a wonderful theoretical idea. So, and now you lowly experimental people just go and implement. So we'll move to the next one because we have no time for this boring stuff. So this is the boring stuff. It's basically all the imperfections we can, well, most of the imperfections and uncertainties in the real setup we managed to came up with. And you can see that for quite a reasonable parameters, the sensitivity, which is this one, of the speed meter, is not significantly compromised. So this black one is the equivalent Michelson interferometer. Sorry. Okay, so the impact of imperfections is not that significant for this speed meter, as we have shown, and this is thereby is one of the best candidates for implementation, because it allows to improve the sensitivity at low frequencies quite substantially, an order of magnitude. Very low. Okay, so that I'm skipping. And fortunately, we come to the summary, which is the repetition of what I've already said, that the quantum non-demolition speed meters allow to evade quantum back-action noise, thereby gives instant access to the low frequency band of gravitational wave signal, which is important for the third generation detectors. Better low frequency sensitivity of speed meters allows to explore the populations of very massive compact objects inaccessible to conventional interferometers, dramatically improve signal-to-noise ratio. Actually, I forgot completely the speaking now as from you. For coalescing compact binary sources, and we can see the more cycles of binary black holes and neutron stars in spirals, which gives us more time to give the warning to the electromagnetic counterpart collaborators. Well, then there is a experimental R&D going on speed meters already, full steam, I hope. So now we understand speed meters in experimental point of view much better. There are no showstoppers so far. There are still some questions to answer, especially in terms of polarization optics. Again, experimental people hate polarization optics, but it has improved dramatically, I would say, in the last 10 years, the quality of the polarization optics. So now this optics already allows get all of the advantages of the speed meters with polarization compared to the Additionally, this is a very economical way of doing stuff because no changes to the main interferometer and to the very expensive infrastructure is necessary. Thank you very much.
Thank you very much. Any questions in addition to the ones that you already asked? Yes, Fred.
There's some magic that demonstrates that sometimes all this low frequency thing, somehow what happened to the basement? Assuming
There is no
that's under control for other people. I missed that, I don't know.
Yes. This is a very, very important. Of course, all I was talking about was only the quantum. So, of course, in order for these to be a useful thing, you first have to deal with the seismic noise, with the Newtonian noise. But this is what is currently in the plans for both Cosmic Explorer and Einstein telescope that they will be reduced. And if they are reduced to the level promised, probably how to do that. But anyway, so if we believe that design sensitivity Einstein telescope and cosmic will be reached, then you will have to do something with the quantum. This is my point.
There's technology, that gives you the confidence that lowering the seismic noise to the point of becoming irrelevant compared to this quantum effect is believable.
Well, it's there is a very old and well-tested technology, which no, just deep underground as we can. That is actually military people know this better. Deep underground, and then you are safe from the nuclear. Also from science. So, and Newtonian noise is also going down if you are underground, because the motion of the object on the surface, and for example, atmospheric disturbances are not penetrating underground. So this is what is the idea of Einstein.
This is well enough calibrated that enough money is doable.
Actually, yes. So there is a very extensive body of research, field research being done on this. And in many, so currently, the main activity in all 3G is going about finding the site, which is seismically very quiet in Europe and the United States. And that is basically what involves the 3G specialists. Gravitational wave conferences are about. Right. So I have a confidence that with enough investment of money and human capital, can reach.
Any other questions? Yes.
I guess I missed the status of the Glasgow effort. So, did you say that the polarization thing was being tried there, or where are they at right now?
Yes. So it is not yet at the point that the interferometer, fortunately, I only one person. So it will take some time. And also the tabletop speaker currently unmanned. There are two PhD students working on it with the projects. So it slows down. Sorry?
One of them is Mr. Frank with the Butler.
Yes. You know it better. Yes, of course. But this was not time. There was no time to include all of this information and itinerary.
But like, are they doing polarization stuff, or are they doing different formulas?
So the tabletop experiment is without polarization. It's a thin case, and it is definitely not a awareness. And the polarization is only steps trying to come out.
And they have looked into like control schemes for the polarization.
That I think is definitely true for the science.
Any other question? Yes, Vicky.
I get more on the information side. Is anything can any of this be tested at GEO or?
Not at the moment.
There's no plan, or it cannot be done because there are other noise sources that are.
This is the main problem. So GEO is and always was limited by other non-quantum noise. So it don't have our ability or power to see whether it's too low.
And do you need a Michelson, or could you do the polarization trick with cavity ferrule? Because like now cavity ferrules have seen throughout the
Yes, you can actually, if you are talking about GEO, you can.
No, not about you. I'm talking about the LSU experiment, the Kennedy experiment that has now seen throughout the But they do the polarization trick and demonstrate.
It is possible. The problem is that you need to do it above the mechanical resonance. Which is not a problem. The main problem is, of course, dealing with the which I talked almost. It is a big step forward.
You have a question? Yes.
Sorry, I might mention that perhaps I missed it. I'd like to go from the end technical noise sources and next to working with incorporate that you have EWP loss at the PPSC. Why is that so much worse than the other sources?
Well, because it is actually the thing which introduces the asymmetry between the powers of the clockwise and counterclockwise propagating. Basically, the ones which which should have a compensating back action. So if you have these two beams having different powers, they have different back action force acting on the mirrors, and they are not subtracted. So this is why the quantum wave plate loss is so important. But 1% is very high values. Current values which are available off shelf is 0.1%, and if you see more, you get the lower.
Okay, so I have a question if there's no more questions. So, as you know, people are also trying to combine squeeze states of light, the current timeline. So, for the speed meter, what would be the prospect for adding squeezing, and what would be the constraint?
The constraints, in principle, are the same as for Michelson spectrometer, injection loss. But speed meter has an advantage, because if you want to do the frequency dependency, so the main problem of the frequency dependency is that filter cavity, which produces the dispersion, the necessary dispersion, the corner frequency very close to, let's say, 30 hertz or something, so very low frequency, which means that the filter cavity should be a very high finesse one. And this means that it is very prone to loss in the speed meter, because this corner frequency is designed to counteract the back action. Because there is no back action, or there is back action, but much slower. The bandwidth of the filter cavity is at least order of magnitude higher in the same bandwidth. So it eases the constraints on the frequency.
So one last issue, in the current in the signal recycling mirror Michelson interferometer, you see this optomechanical resonance, which gives you the 3 dB ponderative squeezing. That
if it is tuned.
Right. So is that something that shows up in these schemes at all?
It is different. So in speed meters, if you use tuning and signal recycling, so you don't have an optical screen,
right?
But rather you have a negative or positive optical inertia.
Right.
So kind of an interesting concept. With the detuning, you can effectively change the mass of the matter.
Okay, well, thank you very much for